We should be live. Welcome to the third day of our summer school in the assumptions of physics. We are going to wait probably another half a minute to see if other people are going to join. And disconnect myself. There you go. Hi, Carlos.
Should we?
Okay, let's start.
Yes, I think you can go ahead.
Okay, so this is the fifth session, and we are going to talk about the things that I haven't fully figured out yet. So the open problems in reverse physics. So this is going to be the session we're going to be talking about quantum mechanics, thermodynamics, and all other neat things. So let's see if everything works. Where is my cursor? There it is. There you go. Okay, so first an overview of what the status is for all the sort of reverse physics approach for all the different theories. So for classical mechanics, as we saw 2 days ago, we are basically, I consider it done in the sense that we have the fundamental assumption. We can kind of reconstruct the things that we want to have. We have a very nice understanding of what the different geometrical objects are, how do they function, and what they mean physically. Of course, things can be always improved. So if people want to help improve there is always space. But to me, I'd rather start building the foundation for all the other for the approach on all the other theories, so that we can get sort of the whole thing moving. There always can be improvement. Improvement is always there. So classical field theory, instead, it's something that we really have no idea on the technical level how to proceed, and we'll see a little bit. We have vague ideas. We kind of have an understanding of what the pieces should be. It's just that on a technical level, it's unclear how to implement it, and we'll see that. In quantum mechanics, instead, I think the core ideas are identified. The last bit was that classical limit, and that really gives us confidence that really the only thing that changes is this lower bound of entropy, which basically means irreducible an irreducible system. There is a hole, but then the description of what's going on inside is below the threshold of what you can detect. So you can't get information about the internal structure, and that's where the cutoff for the entropy is. So there is a cutoff. Below that, you can't get any more information. So that's clearly understood. You just need to actually go through the motion and find all the equivalent characterization of all the different pieces and so on. So that needs to be done. Quantum field theory, it's again completely up in the air, and I'm not going to work on that until quantum mechanics is done and we know how to do classical field theory, because it's just going to be a mess trying to do quantum field theory, because we don't know how fields completely work, and how quantum mechanics should be like really nice and we understood. So, which also means that quantum gravity would be even worse, because there is no theory yet, and the foundations of all this thing are not really well set up. So, but I'll talk a little bit of some idea of quantum gravity still, because it's just again, we know that some ideas that need and how they need to work, and so probably that extension is sort of the obvious thing. Whether it gives you quantum gravity or not, it doesn't really matter. We need some type of things to close the arguments. And then there is thermodynamics, which is in a state that it's a little bit similar to quantum mechanics. I would say a little bit worse, in the sense that we think the ideas are right, but there are some details that I still don't quite understand how they should work. But thermodynamics is a much simpler theory than quantum mechanics, so it's on that level is a little bit easier. So this is kind of the overview. So we're going to go through essentially all of them in an hour, and I'll have to go quick. But these are the type of things that if anybody is interested, we can have follow-up sessions, follow-up live, and start in discussing and kicking ideas of how anybody can sort of have me move these things along. So let's start with classical field theory. And the study is basically, I'm looking for somebody to help me generalize what we have in classical mechanics to quantum field theory. And it shouldn't be conceptually that far away, because you have just to go from finitely many degrees of freedom to continuously many degrees of freedom. And so the main conjecture, in the same way that volumes in phase space, oh, a second, I forgot to, there you go, to light the other light. Okay, so the main conjecture, as we saw, volumes in phase space provide account for the degree of freedom. Volumes in phase space provide account for states and configuration. So we have this symplectic form that sort of does that solves that problem. And the idea should be that volumes in space should provide account for the degree of freedom. So whenever you're counting degree of freedom, you're going to have a state density per degree of freedom, and then you have a volume of space that tells you these are how many degrees of freedom there are in this region, and all the count of states of deterministic irreversibility independent of the degree of freedom should basically be amended to do this. And so what we need is essentially to find a suitable Hamiltonian symplectic formulation of field theory. And it can even be sort of without general relativity, just on E and M. And I'm told that there are, well, I know that there are a couple of these things, and I looked at some of them cursorily, and they're different, like there are a few different ones, and so it becomes a problem of understanding which one is the one that actually works for us. And then this whole understanding needs to be connected to again, how to generalize Cantor state, entropy, and information entropy on a field theory. And even there, I haven't found a way to do it. I haven't found a standard. Oh, this is how you do information theory and a field theory. This is a space of field configuration. We put a probability distribution on it, and we define the super Shannon entropy, because it has to be on done absolutely differently. And but what the assumption is here, the conjecture is that once you have made that connection, all the arguments that we had in classical mechanics are just going to transfer to quantum field theory, to classical field theory, because that's essentially how things should be done. And so just to give you sort of an idea, we talked about the principle of least action as being as the variation of the action being the flow of the states through a surface. So it's basically, again, we need to count states. So that's how the action works. And so let's sort of have an idea of how counting states work. First of all, in the discrete case. In the discrete case, you can imagine to have two variables here. The first variable is the shape, the second value is the color. And now you could have a set of different shapes, which would be different configurations for the first variable. And you ask how many configurations are there, and you basically just count 1, 2, 3, use the counting measure, and you're done. And again, I forgot to change the pointer because it's annoying. There we go. Okay. Same thing, I could have a set of, instead of states, which is this set V, which I'm now, it's not taking at one variable being equal. And then again, how do I know how many states I have? I count them, 1, 2, 3, 4. Same thing with degree of freedom. I have 1 and 2 degree of freedom, I count them. So in all the cases when I'm on discrete variables, I just use counting measures. Now, what happens when we go to the continuous case in classical mechanics, we count configuration using the symplectic form. So we have this surface S, which you should imagine as a two-dimensional surface in a four-dimensional space, which basically is a constraint on one of the degrees of freedom. And the way that you count how many configurations you have, you go and you basically do the surface integral of the symplectic form. So these are telling you how many configurations you have in this piece of surface. Same thing, if you have a volume, now you need to count the states, which are going to be the product of the configuration in all the independent degree of freedom. And so you are going to have a volume form that comes from the symplectic form, and that volume form tells you the state density. At each point, what is the density of states that you have. And so you can see that in both these cases, we're not using anymore a counting measure, because the counting measure would give you infinite. You have infinitely many points, but you're not really care about the points. You care about sort of configuration in some of states on a continuum. So it can't be just counting the number of points. But then you have finitely many degrees of freedom. So how do you count the degrees of freedom? You just use a counting measure. And so Hamiltonian mechanics in this context is the correct count of, gives you the correct count configuration states of finitely many dense, correct count of finitely many dense. No, it's finitely many degrees of freedom. This is incorrect. Now, on a field theory instead, we are looking for something where the degrees of freedom themselves are dense. So the degrees of themselves are continuous, not just the possible configuration on each degree of freedom, but also the degrees of freedom themselves. And you have, in the same way that we have a principle of least action in particle mechanics, we have a principle of least action in field theory. And we would expect that if this was a flow of states, this probably is also describing flow of states. At least that's the simplest conjecture. And so this should be some kind of line integral of vector potential of the flow state density, maybe something like that, where you have not just a density of configurations, but you have a density of configuration per degree of freedom, right? So the number of configuration per degree of freedom is the thing that we need to get, such that we can multiply by the number of degree of freedom, and that's how we would basically count the state. And so the idea is that if I have a volume and I double the sum of the volume, and I have 1 degree of freedom for my field at each point, the intuition should be that if I double the volume, I double the degree of freedom. So it could be, it would be logic to assume that the volume form that we get in relativity, the volume of space, are basically related to how many degrees of freedom that we have. And since we read the Lagrangian as the Lagrangian, essentially the gravitational Lagrangian plus the matter Lagrangian, maybe the idea is that this gives us the flow of degree of freedom, and this is the flow of configurations within and across degree of freedom. That could be something. And sort of the way that I picture in my head is that you imagine that you have a Cauchy surface. So this would be sort of a snapshot of the whole three-dimensional space with the field configurations on top. And then we want to evolve it. And now this point here will go here, and this point here of space will go here. And so if the space is stretched, right, then it's like we are taking the same number of degrees of freedom and spreading it around in space in some sense. And if we are doing that, then you would expect the uncertainty or the range of degrees of freedom on each field to sort of shrink itself. So if I compress the degree of freedom, then I am expanding my number of configuration for each degree of freedom. And if I stretching the degree of freedom, then I am compressing the number of configuration in such that the product of the number of degree of freedom and the density of configuration per degree of freedom remains constant, because we want to have deterministic and reversible evolution. Therefore, the count of the configuration states has to be conserved, and it has to be constrained. So that's the idea, which seems a very reasonable idea, and it seems that it should work. And of course, I don't know enough of essentially field theory in a symplectic formulation and how to put information theory and all this to be able to to do the work. And I hope that it can happen like it happened for the classical limit of quantum mechanics, that I can find somebody else to sort of complement, because again, really going through the literature for all of this by yourself without like it takes forever. So I'd rather work on things where I can be more productive and wait for somebody to help me figure this out, so that we can move the project faster. So that's as much as I'm going to say with field theory. Then we can go and jump to thermodynamics, and there is the key idea in reverse physics for thermodynamics. Probably we haven't identified, and we go through them quickly. And the idea that entropy in physics, it's really the count of evolution, the possible way that things can fluctuate, instead of being the count of macrostates and the count and some sort of information theoretic idea. The good thing is that under suitable condition, you recover those ideas from starting from the count of evolution. So things sort of make sense. And the idea of a statistical equilibrium, basically we can show that it should maximize the count of evolution, and sort of the thermodynamic equilibrium is where all the parts in statistical are in statistical equilibrium from each other. So, and again, this means that there is no information flow, that information went everywhere and so on. So you recover some of those ideas. And one of the things that comes out of this, that equilibrium is fundamental, as is equivalent to requiring that the dynamics of the system does not depend on the internal dynamics and the environment. So we typically have in thermodynamics this idea that the equilibrium, you put something there and things stop evolving. More than stop evolving, I'd like you to think that the system now, the configuration of the system, it no longer cares what's going on at in the internal structure and in the external. So it becomes independent. And of course, if it becomes independent, it means that all this macroscopic quantity has to stabilize, because it doesn't matter what's happening. So that's it. So in this sense, we're looking at thermodynamics as a more fundamental theory, in the sense that you kind of need this type of equilibria to be able to define a system. To be able to define a system, you have to say, okay, these are the variables that I care, and everything that it's in this internal structure and so on, it doesn't matter to me. And also what's happening in the environment, I can kind of define a boundary, and then that's what's happening, and that's it. I don't care what else happens on the boundary. And sort of the idea also of quantum mechanics becomes something like that, because you have the system, the internals are not accessible, you're not going to be dependent on that, and then you have some interaction with the environment, but even again, it's basically just noise. And sort of that's basically the idea. So more than just thermodynamics, this should give us something a little bit more general and a little bit more fundamental than just heat and work. It basically is touches how do we create a system and subsystem, and what is the relationship between all this. So let me give you an overview of this, how it should work. And so this idea that entropy, that process entropy in physics, is really the logarithm of the count of evolutions. You start with the idea that you have a system with a state space, and you can think that is a classical microstate, a quantum state, or any state of a dynamical system that you have in mind, a bunch of variables with some numbers. That's absolutely fine. And then you're going to have an evolution. So you're going to have the state space of the system at a different time. And you are going to get an evolution, which is the complete description of the system at all times. So you know that it passes here, here, and here. And now we can define a process as essentially a collection of possible evolutions. So a process you can think as something that constrains which evolutions are possible. So if you have a complete chaos, then every evolution is possible. You can jump from any state to any state at any time. So you have all the possible trajectories that you can imagine. But if there are some constraints, some forces, and something that is more reasonable, then some of these evolutions are going to be excluded. So that's it, they just go away. So you can think it really as a process, as the space, as a subset of the space of all the possible evolution. And then what we want to have, what we can show is that the description at each time corresponds to a set of evolutions. So if I say I know that at this time I am in this state, then I know that the process from the beginning to end will have to be going through one of these evolutions. And the thing that we're going to assume that we are going to be able to do is count the number of evolution for a particular state at a particular time with some sort of measure, which probably is going to be something more complicated. But for now, in this example, let's just pretend that it's just a measure. So I have a state, and then I say how many evolutions are compatible with the fact that the system at time t is in that state. And so I can have I can count the evolutions here, and it's 2, and I can go and look at the configuration here, and I say that's 2. And now you can just with this, you can start defining a probability, a conditional probability of having a future state given a past state. So, for example, if I want to say what is the probability that I'll end up in this state given at time t plus delta t, given that I was in this state at plus t, well, you say, okay, I have 2 possible evolution. Only one of them goes through this state as well. Therefore, this is just 50% of probability. And so the probability is the measure applied essentially to the intersection of the evolution that pass through both, through one and the other, and over the count of evolution of the count of evolution that pass through S0. So that's basically how you can define it. And then you can say, well, okay, now I can define probability from this overall measure, and I want to define a process, a deterministic process. And a process is going to be deterministic if knowing the state at a particular time allows us to predict the state of the future time. So, for example, if I'm here, I know that I'm going to be here. And if I'm here, I know that I'm going to be here. And so for this process, these are the processes over which we can write a law of evolution. So you can imagine already if the goal of physics is say, oh, I want to be able to write the laws of evolutions in such a way, then you are restricting yourself to deterministic processes. And kind of that's why deterministic processes are so important in physics, because that's sort of, if we want to write this, we need a deterministic process. But there is something that is interesting between the interaction of this definition and the count, because in a deterministic process, the evolution can never split. They can only merge. So if I have 2 states and then the future state is the same, then from then on, the evolution has to be the same. So if we go through the state over time, we can see that the count of evolution per the state as the state evolves can only increase or stay the same. So here we go from one trajectory, from one evolution that goes through here, through 2 evolution that goes through here, 3 evolution that goes through here, and this goes in fact from one, right? So that's the only thing that you can do. It cannot decrease. Conversely, we can define a process to be reversible if knowing the state at a future time allows us to correct the state at a past time. And here you have the dual. The evolution can split, but that can never merge. So if we're here and these 2 came from the same state, then of course everything has to come from the state from then on. So now the count of evolution as we go through the evolution itself can only decrease or stay the same. And so now if you have a process that is deterministic and reversible, now this count of evolution, of course, has to remain the same. And so we have this nice property. Well, we basically said very little. We said that we have states and we have evolution and we know how to count them. And from that, we can already define a quantity that increases or stays the same, that cannot decrease if the process is deterministic, and it's equal if it's reversible, without knowing anything about anything. And now consider that we have a process where the system reaches a final equilibrium. And in this sense, we're kind of thinking of a dynamic equilibrium, but it also works for statistical equilibrium. And I assume that this final equilibrium can be predicted for the initial state. So you have a bunch of states, and then at some point they gravitate, they go towards one, and then once you're there, they stay where they are. So when you are in transition, of course, the count of evolution increases, but once you are at equilibrium, that's it. You've merged all the ones that you can. You can't merge anymore, and so your count of evolution is maximal. And so now we have that for the deterministic process, we have the count of state. Not only it cannot decrease, and it's equal for a deterministic process, for a reversible process, but it's also maximized at equilibrium. And so now this starts really feeling like, well, this looks like a good candidate for entropy. But now one of the things that you want is, for entropy, it's important, what happens when you combine the subsystems together. And if you are in the state space, what happens is that if you have 3 possible states for one subsystem and 2 possible states for the other subsystem, then you just get the product of the 2. And you always get the product. Now, if you are composing processes instead, the fact that you have 3 possible trajectory on X and 3 possible trajectory Y doesn't mean that when you put them together, you have 9 possible trajectories. Because there can be correlations. And so the evolutions in general are not the product, because there can be correlations. But if you assume that the systems are independent, that is, the motion of one does not really influence the motion of the other, then you have all possible combinations. And so not only the number of states becomes the product, but the number of evolution also have to become the product. So when you have the 2 subsystems, the condition on both subsystems becomes, the kind of evolution on both subsystems becomes the product of the individual subsystem. And this is, again, a maximal condition, because if they're not independent, you're going to have fewer elements, you can have more. And so this is not only the case of the independence that you have the product, but it's everything else is going to be below the product. And since we have this product, but we would like to have an additive quantity, well, what we can do, if we just put a logarithm in front of the measure, and then the product of the measure becomes the sum of the logarithm, and therefore the logarithm of the count of evolution becomes additive for independent system and becomes subadditive in all other cases. So now we can define the process entropy to be this logarithm of the count of evolution. We know that it's additive for independent system, and for a deterministic process, it can not decrease. It remains the same if it's reversible, and it's maximized at equilibrium. Right? So we really have now something that looks like an entropy. And then you say, okay, well, does this have anything to do with the type of entropy that we think in physics, like the information entropy and so on? Well, here is how you can recover the idea of the information entropy, the rho log rho. Suppose that a macrostate X is a dynamical equilibrium of the microstates. Basically, this X, like this macro state, is really all the possible ways that things can fluctuate and still keep the macroscopic variable the same. So the macrostate fluctuation can be characterized by a stable probability distribution rho of X in each small delta t. So the probability distribution that we have is really the probability of visiting the state in this small delta t. And again, every time that you define an actual system and you define measurements on those systems in thermodynamics, there is an implicit delta t, which is the time that it takes to take the measurement. So when you make a measurement of temperature, there are some things that needs to equilibrate. You need to explore the system. So there is already sort of a natural minimal time for the macro system to make sense. And so this distribution now becomes what's happening below that threshold of the macrostate, what happens at the smaller scales. And now an evolution lambda t for the microstate, then you can think it as a dense sequence of infinitely many microstates whose recurrence has to match rho. So you have your delta t, which is the sort of your definition that comes from your definition of macrostate, and you can still imagine that there is sort of a continuous evolution there, and you pick countably many points along that evolution. If the evolution has to be continuous, those define, as long as it's a dense countable set of points, they define the evolution, because countably many a set of countably dense points are going to tell you what the continuous thing is. And the idea is that now the macrostate measurements cannot be sensitive to permutation of these microstates. So all the possible evolution, such that the overall distribution of these samples matches the rho, is a possible evolution for the subsystem, and your macrostate processes should be independent of what actually is the realization of the macrostate. It shouldn't be sensitive, because we're only sensitive at the level above. And what happens is the Shannon entropy counts all possible permutation of an infinite sequence, which is delta t, which equals all possible evolution. So one way to define the Shannon entropy is to have a set of things and make all possible permutation on a sequence that goes to infinity, so you have a density of permutations, and that's exactly what we're doing here. So you recover the rho log rho by basically saying, I can think of the evolution of the microstate as an permutation of uncountably many objects. So this is good, because it means so that we can recover what we want to recover. And so the idea is that this macrostate, this equilibrium at the macroscopic level, you can think it as a tube, right? And you're jiggling around inside the tube. And when we are describing, it doesn't matter which actual realization within the tube you have, because all you care is what tube you picked, and the tube is fully defined by the microscopic quantity. And so the idea is that you can think of this equilibrium as the evolution decoupled from the environment and from the internal dynamics that are going to be responsible of the oscillations within that tube of evolutions, and that's basically what we're trying to do when we're describing this type of equilibrium. So if this works and if this makes sense, then we should know that we have no mention uncertainty, disorder, statistical distribution, lack of information when we define the basic concepts, and therefore these concepts are not fundamental in this context. Actually, the thing that was fundamental was that we had a dynamical system, and without law of evolution, like not even a dynamical system, we had a system and a set of possible evolution and the ability to count them, and that was enough to define these objects. And then in different conditions, we found some properties, but the property in the sense at a fundamental level is just there are some possible evolutions of a system, and that's it. We also have not discussed what type of systems or states we have. Therefore, everything we said in principle is valid independently of the type of system. And the goal here would be, the stretch goal would be to create a sort of a generalized type of thermodynamics that explains why a lot of the thermodynamics idea and information theoretical ideas are present in biology, economics, evolution, and so on. Like these concepts are being used a lot more than just in physics. And so having a sort of a general theory of why that is and what is it that it's describing, I think it would be nice. And then, again, the idea is that the process entropy increase, why the entropy increases in time, is explained by definitions and the setting, the fact that we have a process with equilibrium that depends on the initial state. And so this type of explanation, it's really a definitional explanation. We are looking for the things that has particular properties, and therefore we have these consequences. And the explanation is, to me, straightforward because, as I said, all that requires is being able to assume that we can count these things. And there is no mechanism. So any mechanism for which you get a process that has this equilibria, and that gets the correct count in the same way, it's fine. So again, this sort of matches a lot of the other insight that we had in reverse physics, where a lot of the stuff that we got in classical mechanics, like the action principle, we don't have it because there is a process that finds the action. No, because it's just the expression, the re-expression of some other conditions that you've put on the process. So these are sort of all hodgepodge ideas, which it's exactly why they are open problems. But just to give you a sense, also this can allow it to recover the thermodynamics if we further constrain what are the states and the system that we're looking at. So if we assume that states are equilibria or faster process scale, then each state will have a well-defined entropy. If you assume that states are identified by extensive property, and you assume that if this quantity is the energy, then you get the existence of an equation of state, because given these extensive properties that fully define the state, you need to have an entropy because these states are actually equilibrium. From these, you can define the extensive quantity. This is basically the Gibbs approach to thermodynamics. You have an equation of state in entropic form, you define the intensity quantities, and then you can define your differentials, and you can recover your usual relationship. And what you're actually doing when you're studying your heat engine with a reservoir and a mechanical system, you basically are trying to understand the interplay of energy and entropy. So you have a reservoir, and a reservoir is a special system where the energy is the only state variable, and the entropy is a linear function of energy, right? This function here is a line, and therefore all the energy is stored in an entropy. And so if you increase the entropy, if you increase the energy, you're going to increase the entropy, and so you have this relationship. On the other side, the mechanical system, you have the same entropy for all the states, right? If you, no matter what you do, the mechanical system does not have a different entropy, because you need to be able to put the energy in and get it back, so that the entropy cannot increase. So there is no energy that is stored in entropy. And if you were to calculate the beta for this, right, because the beta is simply the derivative of the energy respect to the derivative of the entropy respect to energy, and since the entropy is a constant, this would be zero. So in this thermodynamic setting, the mechanical system is like it has infinite temperature, and therefore you can take something from a mechanical system and put it in a reservoir because you're going to a lower temperature, but you can't always do the reverse, because it would be like taking something at a finite temperature and put it at infinite. And this also tells you why sort of negative temperature, the betas that are negative are sort of very difficult to see, because the mechanical system now is lower than has a beta that is lower than temperature, sort of in some sense lower than all the other negative temperatures, and so all the energy now wants to go to the mechanical system and they get out of the states with negative entropy. So anyway, this can be done. You can recover things, and so if there is anybody interested in helping me figuring out how to clean up all this stuff, that would be great. Now, the other part is, of course, quantum mechanics. And as I said, in quantum mechanics, we have ideas that are a lot more well-defined than we have in the thermodynamics. So it's clear that irreducibility and lower bound of the entropy is the only ingredient that makes quantum mechanics different from classical mechanics. The problem is show it in a clean way, and that's where I don't even know whether we have the correct math to be able to do that, so we sort of have to become a little bit more inventive. So the goal here is essentially to develop a minimal interpretation that is based on what and only what can be settled experimentally. So no talk about hidden variables and multiple worlds or whatever people like to talk about. What everything has to come out of is that states are ensemble, either pure or mixed, at some sort of equilibrium where the internal dynamics and the variables can be ignored. So and that's essentially what puts this lower bound on the entropy, that if you were to go and know more about what's happening and get a more complete description, then you would have to know about the internal dynamics and the environment dynamics, which you said you can't explore, or it's completely independent, and therefore you can't really get any information about that. The core, the gist of everything is that projection, you should really think them as process of equilibrations, and we'll see why. And that unitary evolution is the deterministic and reversible dynamics, which can also be recovered as a quasi-static evolution. So you see, I'm talking about, I'm using terms that are very close to thermodynamics to actually describe quantum mechanics, which is kind of the point. We should be using and recovering quantum mechanics and not from like very strange ideas. Like this is the problem that I was saying 2 days ago. This is similar in spirit of what many people do with reconstruction of quantum mechanics. The problem is that if you go and look at at least all the reconstruction that I've seen, at some point they have some mathematical requirement that it's not clear how you would justify from the physics. And here we're striving to use only physical concepts that are already there in our physical theories, so that we have a nice intuition for those, and sort of they work, they make sense. And I do think that all the elements are there, scattered in all the different papers and videos and notes. They just need to be all put together. So let me tell you a little bit how it works. So in quantum mechanics, projections are very important, and mathematically projection is a linear and idempotent operation. That's what defines a projection. Now, imagine that we have a process like the measurement process, right? You have a state that comes in, and then you have the possible eigenvalue of your measurement, right? And you go there with a given probability, right? This process is linear in probability, in the sense that if I have a mixed state, then I can decompose the mixed state into pure state, apply the process on each of them, and then sum the output. So the process of the measurement process on the mixtures is equal to the mixtures of the output of the measurement process. Now, what does it mean that it's a projection? It means that if I repeat the process, the same thing that I had at the beginning, I get exactly the same. So I get the same result, meaning that a possible output of the process, if put again through the process, it gives you the same thing. And again, we already have a name for a state that if you put that is unchanged by a process, which is an equilibrium. So a measurement process is something where all the outputs are equilibrium of the process. And now you can also reason it in the opposite way. If you have a process such that all the outputs are equilibrium of that process, that's a projection. So instead of thinking of measurement as projection as measurement, and measurement being special, you should just think as measurement as projection, as processes whose output, all the outputs are equilibrium. Therefore, a projection is an equilibration process, and a measurement is also an equilibration process, because you want the output to be stable, to be sort of in a sense, the measurement process to be repeated. And again, we are talking about equilibria. Can we make a parallel with thermodynamics and statistical mechanics? And of course we can. So suppose that you have an open glass of water. The number of particles is not well defined because it keeps fluctuating, but the chemical potential, the volume, and the temperature are well defined. But now suppose that you want to have the number of particles well defined. How would you do it? Well, you put a lid, and now putting a lid on changes from a grand canonical to a canonical ensemble. You are going to have a probability to end up in one of these things, but then when you are in one of these states, you know that the number of particles is now fixed. But once we fix the number of particles, the chemical potential is not defined anymore, because the chemical potential really tells you how the system is fluctuating, and the system is no longer fluctuating in number of particles. Therefore, the chemical potential makes no sense to be defined. And now you can compare this to what happens during a spin measurement. You prepare a particular direction of spin, meaning that you've put the system in an environment where there is a vertically aligned magnetic field and the thing has equilibrated and now it's pointing up. And now you do a spin measurement. What does it mean that you spin measurement? You change abruptly the magnetic field. Essentially, you change the boundary with the system, and you're forcing the system to pick one or the other. And once the system has picked one or the other, it has to stay where it is. So this is the same thing. At the beginning, there is one variable that is defined here, and there is one variable defined here. You force the system to change abruptly, and now you're going to have a different set of variables that are well defined. And so the idea should be the quantum constants are just different boundary conditions. And what you are doing during the measurement, you're doing something that is akin to what happened in thermodynamics. When you change the type of equilibrium, you have an abrupt change of the boundary condition. So that's one type of evolution. If you assume that you have a unitary evolution, that you want to something that is deterministic and reversible, what you find from simple calculation is that you are going to have a Hamiltonian that tells you how the system is evolving, because the change of the system has to depend on the previous state of the system. And in this case, the final state has to be normalized, and therefore you get that the time evolution has to be, the generator of the time evolution has to be an Hermitian operator. So in general, then, you can imagine that any process, deterministic or stochastic, has to be linear in terms of the ensemble. Whatever statistical mixture we put in, the output has to be the statistical, the mixture of the outputs. And you're going to have two types of processes, one that are deterministic and reversible, that gives you this unitary operation, and other ones that are equilibrations, and which are projection. And both of them are idealizations, in the sense that deterministic and reversible evolution means complete isolation, which you're never going to have. And also equilibration, and maybe it's something idealized. It doesn't really work like that. There is something in between. But in some cases you use one, and in some cases you use the other. And in this sense, since both are idealization, it's not that one is more fundamental and one has to be reduced to the other. In this sense, there is no measurement problem, because there's no question as how nature chooses which process it has to use. Nature does what it does. We have these two models that are idealized, and sometimes we use one and sometimes we use the other. Now, what is more interesting, though, is that when you define the Hilbert space itself, you are mathematically defining all projection. So mathematical Hilbert space is a Banach space plus the projector on each subspace. So there is no, technically, when you're defining a Hilbert space and your state space in quantum mechanics, since you have an inner product, you may not define a deterministic and reversible evolution, but you are always defining the equilibration. So you are always saying that there is a projection for each subspace, meaning that there exists a way to equilibrate every, to make such that every state is the output of some equilibration process. And that basically tells you this idea that I was saying before, recovers this idea that every state is some sort of equilibration. And what you can do is that you can recover unitary evolution as a sequence of infinitesimal projection, and basically as a quasi-static evolution. So the way that you can think then quantum mechanics is you have some states. States are outputs of black boxes, and your black boxes are these equilibration processes. And then you put them one after the other, and you make this quasi-static evolution. And this also makes sense to what you do, for example, in field theory. In field theory, to calculate the scattering processes, you put the initial state at minus infinity and the final state at plus infinity to describe something that takes far less than a femtosecond. So it's clear that you are substituting the real process with some other process, but these are the type of things that we also do in thermodynamics, and so it makes sense that this picture sort of agrees with what we're doing then at this level. So So this is basically the idea. We have black processes with equilibria that allows you to define states, because states are equilibria. You get the projection, you get the state space, you get you do a quasi-static evolution, you get deterministic irreversible evolution, and from that you get unitary evolution. And so you have that every preparation is a measurement, and so time evolution prepares the system at each time. So it's like, you know, I prepared this state, but then time evolution is going to prepare the state at each of the other steps. And so if we think about these projection, not just as measurement, also preparations, then time evolution is a series of measurement and a series of preparations, because each preparation is a measurement, and all of this sort of can be made self-consistent. So that's what we are shooting for. And of course, as I said, there are lots of other details to be fleshed out, but I do think that this makes the whole thing all consistent without using a lot of the weird things that comes out in the foundation of quantum mechanics. So since the time is running out, and there are probably going to be lots of questions on this anyway, we can go at the last few things. So for quantum field theory, as I said, we should first do quantum mechanics and classical field theory before talking about this. But I did want to sort of continue that idea of counting the states, because I think you might have some insights of what needs to happen when we quantize. So let's see. Okay, so one of the ways to show that sort of a lower bound on the entropy has to break, in some sense, the classical ways of thinking about states and so on, comes from this sort of problem. Suppose that you want to count states on a continuum. So you have a real line, and you want to count the number of configurations on the real line. Now, you would like to say that each state is a single case. Each point on the real line counts as one possible configuration. You would like to say that a finite continuous range, since it carries finite information, will have finitely many configuration as well. You know, there is 1 meter worth of configuration. You would also want that the discounted configuration is additive over disjoint sets. If I have a set here that it's 20 configuration, and a set here that it's 200 configuration, and they're disjoint, when I put them together, I get 220 configuration. Now the problem is these are clearly incompatible, because if every state, if every configuration counts as one, and a finite range has to be additive, you would get that the finite range has infinitely many points, and therefore it has an infinite measure. What happens in classical mechanics is that you discard either the first one or the second one. If you discard the first one, you get a Lebesgue measure, which is what you typically use to count configuration of a continuum. And if you discard the second, you get the counting measure, which is what you use to count configuration on discrete sets. The problem is that what you do in quantum mechanics instead, you must give up the third one. That's sort of what happens. So if you imagine that you have the block sphere, right? As we saw in classical mechanics, you count the configuration with the logarithm of, so the entropy is the logarithm of the count of configuration, and as we saw before in our presentations, you can also define the count of configurations as the exponential of the entropy. So if you do this in quantum mechanics, if you get a point, each point, right, each point A and B, would have on the sphere, on every pure state, has a zero entropy, therefore the exponential of 0 is 1, so every point will count as one state, which is what we want for the single one. And if you count, if you get the whole block sphere, right, the block sphere has the maximum entropy that it can give is given by the center of the block sphere, which is going to be 1 bit of entropy. So if you take A and B and put them together and make a mixture, you can reach 1 bit of entropy, and therefore 2 to the 1 is 2. Therefore, the set of A and B now counts at 2 states, which makes sense. You have 2 orthogonal states, they are perfectly distinguishable from each other, and that's what you get. Now, if instead you take 2 elements that are not orthogonal, then you can't get the full one bit of entropy, you get less. Therefore, the count of configuration is less, if we use this measure to get it, it's less than 2. So the idea, again, that the set of A and B gives you two completely distinguishable number of states at everything else being equal. But A and C, if you take two things that are not orthogonal, then they're defined in different contexts. These states are defined in different contexts. So they are different states, but they're not completely distinguishable from each other. So they don't really count as two complete and distinguishable states. And this is sort of how quantum mechanics solves the idea that we want the states to count as one, but we still want to have a continuum such that we can transition from one state to the other in a way that it's it's smooth and differentiable and so on. And so this is why sort of all the probability feels weird in quantum mechanics and so on, because you're losing this additivity property. Now, what happens, and this is again the conjecture, is that you're going to have the same problem if we want to have a measure of number of degrees of freedom and counting the number of degrees of freedom as a region of space. So again, since we have a degree of freedom in a field theory, every degree of freedom in a point, we would like that every point is a single degree of freedom. We would like to say that at this specific point in space, there is 1 degree of freedom. And again, we would like finite volume to have finitely many degrees of freedom and the measure to be additive. And we are going to have the same problem that we would have when we were counting states. And therefore, it's not like in the transition from classical mechanics and quantum mechanics, it's very destructive because you have to change this idea of additive measure. It's very likely that you're going to have the same problem if you want to put a lower bound on the degrees of freedom count, because it's not going to make much sense that in a region of space you have less than 1 degree of freedom. And so what's going to happen, in the same way that the states should be counted if they're distinguishable, and you have two states that are not fully distinguishable, and therefore they're not really two states, the measure does not count them in two. Something like that should happen with points in space and degrees of freedom. If I have 2 points in space that are very distant from each other, then yeah, the configuration of one is going to be independent from the configuration of the other, and then we should say, okay, those are truly independent degrees of freedom. But if we put them closer and closer and closer, at some point, you're not going to be able to say, oh, yes, these points are independent. At some point, they are going to basically become the same degrees of freedom, because they're so close to each other, and you're not going to be able to put something different on the others. There's going to be a strong correlation between them, and they're not going to be independent. So if we want to really have a lower bound on the number of states, like we have, and therefore a lower bound on the entropy, like we have in quantum mechanics, it would make sense that if we want to have a count of the degrees of freedom as the volume, we are going to have a problem to just use a Lebesgue measure for the count of degree of freedom, because you do not have a lower bound on the number of degrees of freedom. And so the conjecture here is that maybe this is the conceptual problem that you're going to have when you're trying to mix quantum mechanics and a proper field theory that does all of this. And it should make sense that it's a lower scale that you're going to have this problem. And so this is sort of a conjecture that I have, that if while we are building the whole in physical mathematics, the theory of ensembles, I'm always watching out for this problem to understand how this can be solved, and if it can be solved. Okay, so basically these are a bunch of things that are still need to be figured out. And if you're interested in building a conceptual framework that treats physical theories, models, and physical and nothing else, and you want to help, I'm always looking for people to help. The simplest thing, if you have a particular knowledge in any field, if you plan to build the knowledge in a particular field, or even if you want to say, I'm just going to help review material so on. We have a form on our website. If you go to help contribute, that you can fill in and say, these are the things that I'm interested in, these are the things that I can help with. And then when I'm going to do a live, when I'm going to do something, or I have a problem, I can contact you and say, okay, let's go and discuss this. And then if you want to be more involved, then I'd suggest that you join the Discord server, and we can start interact more to see what can be done. So that was the hour, and that's it. Open up for questions.
There are already a few in the Q&A. From Carlos, for classical field theory, my intuition is that everything that worked for point mechanics should translate according to the following correspondence. Position becomes field, conjugate momentum becomes conjugate momentum of the field, time becomes event, and integral on time becomes integral on a region of space-time. Is this incorrect?
It's a little bit more complicated than that. So for the conjugate field, I found two formulations. One that has a single conjugate field, one that is a vector of conjugate field for each of them. And the one that has a vector for each of them actually might my nose tells me that it's the one that works that is more covariant, because what you need to do, remember no, because you haven't seen it. The way that we recover the structure of phase space is that you have this relationship between position and momentum, such that position defines the unit, and momentum is defined as the units of momentum are the inverse of position. So Q defines the units and P have inverse units. So when you multiply them, the unit disappears. So you have a unit independent quantity, and that is going to be the counter state. So you have a counter state that is independent on the units that are being defined. Now here we have three things. We have the unit of the field, we have the unit of conjugate, and then and these sort of are going to tell us, as I was saying before, some kind of density of configuration per degree of freedom, because then we need the volume and we need to multiply the volume. And so the question is, where does the unit of the volume go? If it goes so the idea is probably is going to be on the conjugate field. So you have the field that defines the unit of the configurations. You have the volume that defines the number of degree of freedom. But again, it has to be a volume in space, because time is not going to give you more degrees of freedom. And then you need a conjugate, and the conjugate needs to sort of cancel out both the units of one and the unit of the other. Meaning that if you have some change of units in the volume, the conjugate field also should change. Like if you stretch the volume, then the conjugate field should shrink. So these are the things that are absolutely not clear to me on how they should work. But I know that from unit consideration, they should kind of work like that. So these are the pieces that need to be figured out. And again, the standard math does not show these things, because the standard math takes the units and throws them out and pretends that they don't exist. Instead, all the things that we were doing in reverse physics, all the insights that led to those things, is because I was taking care of the units. And so here I need to understand what happens to the units so that I can have a count of configuration that it's independent of the units of the field and of the units that we give to space and time.
Right, the next question is from Thomas Oudeville regarding the evolutions, count of evolutions. I find this quite surprising. In an ODE, the curves can never cross each other or merge. Do you consider different kinds of evolutions than usual?
Right. So if you have an ODE, you have some type of deterministic reversible scenario, right? For every point, you have another point. And so in that case, these are the things that need to be, as I said, that need to be understood, and because what we showed were example in the discrete. How everything needs to work on a continuum is a little bit to be understood. So in an ODE, you're going to have also the problem that solutions can converge to a point. So they don't intersect, but they become more dense. And I do think that the entropy should qualify that, should understand that, because at the end of the day, what you're looking is areas and how they shrink and so on, right? When you have a dissipative system, right, in classical mechanics, there is an ODE, the thing spiral maybe at an equilibrium. It's not that they actually go to the equilibrium, but you get denser and denser around the equilibrium. So those are the pieces that needs to be fully understood.
Next question is from Tobias. A Hilbert space is a Banach space plus all possible projections. Mm-hmm. Does that require completeness, or is this just defined through the inner product?
Defining the inner product means having all the projection. It's exactly the same thing. So the completeness is given by the Banach space. So Banach space has a norm, and the topology is complete with respect to the norm. Then you're adding what's it called? An inner product that is consistent with the norm. Therefore, if you were incomplete with the norm, now you're complete with the inner product, and you're adding all these projections.
Next question is from Xinyue. The slide seems to suggest that we can reconstruct Shannon entropy without probability distributions. How to understand this?
No, you need the probability distribution to reconstruct the Shannon entropy. So what you do for the permutations is you have a probability distribution over some elements, right? And then you have you do a choice of countably many by picking one at random according to the probability distribution. So if you have, let's say, something simple, you have head or tail, right? And then you sort of flip, you have 50% to get one. You imagine all the strings of a head or tail taken at random from that distribution. And then you basically go and count them and do, you basically count them for any n, and then you make the n go to infinity. And you're gonna get the density of the states. There is something wrong going on with my screen right now. I'll fix that later. Okay, I lost the slides. So that's basically how it works. I have a video on YouTube that actually goes through this definition, where I have all the like the 3-4 different ways that I can recover the Shannon entropy. One of them is through the permutation. So you can go and look at that if you want all the details.
So the next question is from Daryl. Are you taking PhD students? It has been upvoted. And
yeah, I'll leave that to the professor to respond to that.
You're leaving it to me. So the primary issue is funding, really, for this research, as you might imagine. There isn't really government funding that funds this type of very foundational work of revisiting the very low-level foundations of a lot of existing theories. So yeah, right. We do have an external grant right now, but the funding situation is very limited. So that's basically the main constraint in taking on PhD students formally through the University of Michigan. There could, in principle, be possibilities working with others who are primarily affiliated, who are getting their degree issued and financially supported through another institution. And we would be able to work with them potentially if we found a project of common interest that would be acceptable to their home university. So that could be a possibility. And of course, we're trying to find other sources of funding so that we can expand opportunities in the future and just get more people involved. As Gabriele has been saying, we really need to build up a larger community. It's really large, ambitious project. So we need more people to be involved to carry out this program. See, there's a follow-up. What about undergrads at University of Michigan? That is much easier. since undergraduates can do research for credit, so we do that relatively often, work with undergraduates for typically for research credit. And we've had I guess two so far officially do their senior theses or honors theses on the project. Tobias points out that he is currently a PhD student working with us here at the University of Michigan, who originally found the project through YouTube, and a couple years later reached out.
So in principle, we do take PhD. The problem is that you might have to teach to get the what's it called, the support, and there are all these details that, again, Christine knows more than me.
Those are all the questions in the Q&A.
So I'm happy to talk more about anything. So if somebody wants to give me a topic, I'll start talking. So.
Skipped a slide. Robbie asks, how much topology should I know to pursue fundamental physics?
How much? Is that the question?
How much topology?
How much topology? Good question. So for me, the main problem is not really knowing like deeply about the subject, in the sense that topology quickly becomes a lot of things that we're never going to be interested. So just to give you an example, topologies are also defined on, so the topology that we are interested in are all T0 and second countable. There is a lot of work on other topologies that are not second countable and not even first countable, right? And there is a lot of literature about that. So you're going to be interested in that? Absolutely not, right? So it's very particular what are the things that we should be interested in physics and what shouldn't we? And part of my problem was, when I started working on this more in detail, was basically that. Should I be interested in that? Should I not be interested in that? And that's where, going both from the physics and both from the bottom, you start having a clue. So for topology, for me, the thing, it's funny because I only understood, for example, something that I think everybody should understand, like a month ago, which is the connection between topology and limits. That would be a much better way for if you're doing physics to understand topology, because understanding it as a notion of limit instead of all the other things that are said would allow you to understand what it actually is, because a lot of the time topology is used in physics as basically the things that allows you to count holes in a manifold. And that's not how mathematicians think of topology. And then there are issues that there are tricks that you can do in topology, that it's a little bit like taking, I was saying that taking real calculus and taking a real integral and transforming a complex variable and do the calculation there because it's more convenient, right? So there are all these tricks that have to do with compactification in topology that are very important in topology. There are lots of results on those things. And again, if you're doing a calculation, maybe they're going to be useful. But then if you want to have this idea that, I want the math to be meaningful and I want these things to actually be something real, then you realize that a lot of those tricks are like you should never ever do them. So the compactification is basically this idea that you take a space that it's not compact, which means essentially you can't always cover it with finitely many pieces. Essentially, that's the way that you can think about compactness. And you add some points, and then magically the thing becomes compact. So, for example, the circle is compact because if you have open sets that cover the whole thing, you can always do it with finitely many open sets, open intervals. Now, the real line, instead, it's not compact, right? Because you cannot always cover. If you start with countably many sets that cover the whole thing, you can't throw some out and get finitely many. You always have infinitely many. But you can understand the real line as a circle if you add a point to infinity. So now you have compactified the 1 point compactification of the real line is the circle. But adding the point of infinity in physics, you would be like literally saying that infinity is a possible value for your variable, right? Which of course that doesn't make much sense. And so the issue for me is really understanding when these things are mathematical tricks, when they have physics in it, and so on. And again, you don't need so much. Like it's a different problem than a mathematician does. So if you go and follow a course in topology from a mathematician, this is going to tell you all these different things, all these different tricks, and so on. And I kind of feel that we should have a sort of a class where, as a physicist and engineer, and so on, you're taught the bare minimum of what these things are and how they apply to sort of conceptually to physics and so on. And that's basically what we should have. And it's very difficult to do now, because if I tell you, oh yeah, you should definitely know some topology, right? And then you say, okay, I'll go and get a 2-semester class in the math department, so I really know topology. That's probably an overkill. But it might be that you need, pieces from the first semester and pieces from the second semester. That's kind of so. What I do for all these things is I take math books, I go through them quickly to just get some idea of these are the pieces that I need, and then I go and study the particular chapters that are needed. And it's the same for everything else. Order theory is the same thing. Like you need to understand some, because it's one of these fundamental things that keeps recurring, but it's difficult to say, oh, you need to know order theory or topology like a mathematician. So
I can add to that. I think long term it would be valuable if we had more people involved in the project to create a textbook, basically a mathematical methods in physics textbook that would be oriented toward the assumptions of physics program. Of course, you still need other things like, vector calculus or, although I guess we would teach that a bit differently. So it's not that you don't need the materials typically taught in a mathematical methods for physics class. We typically have those types of classes, at least in the US system of physics education, where you do exactly that. You say, well, you need to know some of some particular mathematical topic, but you don't need a full semester course in the mathematics department on that. So we're going to do 2 weeks on this math topic, 2 weeks on this topic, 2 weeks on this topic. So we would want to redo that course for in line with the assumptions of physics project, or expand that course.
And if we had people, if we can build a community that helps us build that, I think that would be very valuable.
Yeah, that would be valuable. That's definitely an area where I could imagine other people coming in to contribute, because it's basically taking the ingredients. They don't have to develop new ideas or new math, right? It's really organizing, identifying exactly what topology is needed, what measure theory is needed, what order theory is needed, and writing it up succinctly aimed at physicists, students in physics. And Thomas Sartoni has a direct follow-up on that, so let me skip to that. More in general, what mathematics is actually necessary for fundamental physics? As a beginning student, the landscape is so vast, it's hard to get oriented in it.
Yeah, not just for a beginning student, for everybody. And what happens is that people sort of just ignore the method that they're not used to, or they don't immediately see. Yeah. I mean, that could be, I mean, so for all these things, if people are interested, we could start having live discussions where you're not actually in a chat, you're actually live, and we can talk more with a bigger bandwidth, and start making the landscape. And I can tell you, look, these things are certainly pieces that you need. These pieces are certainly pieces that you need. These you should be aware that they exist, such that you at least know why you're not interested in them, right? So, for example, all of the definition of how infinity is defined in terms of ordinals and cardinals, I think you should know about that. But you should know about that not because it's important. You should know about that because you know exactly why it's not important. And even that is important if you're doing fundamental physics at this level, to know why and what is it. Because like I hear talks of people that present at conferences that clearly don't understand these things, and they say such nonsense that you should at least have the background to see that and say, okay, that's not going to be interesting. Because otherwise, the issue is that you might get fascinated, all these concepts and so on, and then you're just going to waste time.
Shinue has a question. In the quantum mechanics part, we seem to have quantum measurements being understood as parallel to thermodynamics measurements. But how does this resolve different observer issues?
So there is no issue of different observers, in the sense that the only thing that can, so this is where, again, there is a fundamental confusion on the role of entropy and the role of probability in physical theories. So yes, you can use probability to have expectation in sense of credence and all of that, right? And but that's not what physics is about. I mean, if there is a measurement and one measures something, everybody else measures the same thing. Now, you're going to have the problem of incomplete information, in the sense that there is some kind of mixed state, and I know more than you, right? But that just means that if I have my mixed state and you know more than me, you have a distribution that is sort of a component of my distribution. So my distribution is your distribution plus something else. Since both classical mechanics and quantum mechanics are linear theory on the probability distribution, and so therefore mixtures of evolution is evolution of the mixture, there's not going to be a problem either on the unitary evolution or the projection, the measurement, the equilibration. Everything is going to work. So there is no sense that people have to see different things. Now, there are all these other issues of Wigner friends and all of that, and Schrödinger cats and all that. But also all of those become moot when you understand that, again, there are quantities that are defined on ensembles, like temperature, like average energies, and all these things that are the macroscopic quantities. There are not things that can be in superpositions and stuff like that. They're just averages. You can't make a superposition of averages. It just doesn't make sense. And so a lot of the problem that come out from interpretations as they all come out of multiple observers and so on. Or they all come out because you are trying to give the mathematical object some meaning that it's problematic. And so one of the problems that you're going to encounter, for example, if you take the pure state as being the complete specification of one system, so one instance of a preparation at a particular time, you're going to come, you're going to get into all sorts of problems. But if you say, like we want to say, that even the pure state is an ensemble. So when I say spin up, I have the state spin up. It's not that I have the full description of a particular system. I'm still talking of the output of a procedure that always prepares this state called spin up. And so in that case, yes, my spin is always up and so that quantity is always well defined. But the preparation of all the other observables, there's still variability there. In the same way that you prepare your macro state with a particular chemical potential or particular temperature. A particular temperature, yes, the temperature is set, but the energy is fluctuating within your small delta t. And so it's not that everything is defined. You have an ensemble, and the ensemble is this infinite collection. And therefore, this variability that you have, you can think it as a variability in a small delta t, and sometimes it's a variability in a small delta t, but sometimes it's just a variability that, every time that I prepare, I'll prepare the same thing. And so once you start looking at things like that, a lot of the problems that people have, to me, they sort of disappear. And part of doing the reverse physics and this minimal interpretation for quantum mechanics will be to do the due diligence, to go to the literature and philosophy and say, okay, all these problems are the people that claim that there is, and you say, okay, in our interpretation, in our setup, this doesn't apply because of this, so this is resolved like that, and so on. So that becomes sort of detail. But my main intuition is that all these things are going to resolve themselves.
Daryl asks, if we lose additivity, we no longer have a measure, right?
Yes, you have these things that are called the non-additive measures that are weird because a measure should be additive, but there's a field called the non-additive measure theory. And it's very developed in decision theory, fuzzy logic, fuzzy sets. They all use non-additive measures. We were hoping that the type of non-additive measure that we are interested in were those types, and it turns out that they aren't. So then basically, it's another piece of math that I think we're missing to be able to study these things.
They're also more generally called set functions, right?
Set function is sort of the proper term for any function that you give it a set and you have a number. Then typically you want these functions to be at least monotonic, and so that if the set gets bigger, the number cannot get smaller. And these are sometimes called the capacities, as you will see later, because we call them capacities, but they are also called fuzzy measures or non-additive measures.
Lama asks, would you be open to get me in contact with Jacob Barandis from Harvard? I plan to work on his recent research topic soon.
I already tried to contact the guy. So I saw his presentation on his stuff like years ago. And I had some technical questions because I didn't understand at a measure of theoretic level what he was doing in probability, because he's doing probability like a physicist. Probability is a function that I integrate over, it's a probability density, but then that doesn't tell me some things. And he wasn't able to answer my questions. Then I also tried to reach out to him again. What was it? Last October, because he was supposed to be at a conference that I was also going in September, but then he wasn't there. So I tried to reach out because I still wanted to understand it. But then, yeah, he sort of disappeared again. So.
A question from Arnav. What are your thoughts on the paper by Professor Renner? Quote, quantum theory cannot describe the use of itself.
So I don't know that paper, but I know of a lot of people in philosophy that that try this thing of, can you describe the fact that you're making measurement in something? So this circular thing. I do not know whether that's a valid question in general. That's my problem, in the sense that, as you saw before, the theory, any physical theory, you need to define a system and an environment. You're going to have a boundary between the system and the environment. In thermodynamics, it's always clear that you have a boundary in the system and the environment because it's part of the specification of the system. my argument is that even in quantum mechanics, you have a boundary between a system and environment, and that's the context, right? So the quantum mechanics is contextual because the context, because you need to define the relationship between system and environment, and during the measurement, it's more important because the measurement is something that is happening in the environment that is going to push the system in particularly defined states, right? And so if this is the case, and you also consider field theory something like that, I have a region of space, and there's all this stuff like that. I can't see any way at a conceptual level what it would mean to close it in that sense, so that the thing can describe itself. Because clearly, quantum field theory cannot, if this region under this constraint of an environmental boundary cannot tell me what's happening outside, because I made the cut. I'm only describing the system under these conditions. So to me, it's a whole can of worm that it would need to be well specified, but quite frankly, it's one of those pick your battles, right? I only have finite time, and I'd rather spend it into figuring out the things that to me have a much better chance to be solved and addressed than these other problems that I don't even know if they can be solved.
We are at 11:31,
yeah.
So to move on to the last lecture. I don't know if you need a minute or...
I have half a bottle of water, so I think I'm good, but I need to change the slides. So let me do that. And this is it. The same shortcut did both. Okay, so we are still everything good. Okay, so let's start the next section where I will talk about open problems in physical mathematics. So here there's going to be a lot more nitty-gritty details of mathematical stuff. Again, we should probably start with an overview of how things are and where we would like them to be. We are going to basically, so there are basically three layers of things that we'd like to have, if you remember from the talk 2 days ago. We have a layer, the most fundamental layer deals with experimental verifiability, the fact that a physical theory needs to be grounded in experimental evidence, and therefore we need the verifiable statements to define our physical theory. And this part, and of course, I forgot to put the pointer options again. There you go. So this part is basically it's basically done in the same way that I consider classical mechanics done. There is probably details that could be done better, but for finite time, I'd rather start working on the other pieces and start putting the other piece in the ballpark. Then there is going to be another piece that I think is needed, which I call information granularity. That is basically the part that should define in general what a physical dimension, what units, and therefore connected measures are. And this is basically just vague ideas. I had a starting ideas. I was able to kind of characterize the problems a few years ago, but I was able to make very little progress. It was also fun because this uses order theory a lot. And then I contacted a professor that wrote a very good book in order theory, basically saying, well, I'm trying to do some of these things. Could you have some hints on what I should be doing and so on? And I didn't hear from him. So I said, okay, that's 90% of the emails like this don't get replies, so it's fine. 3 months later, I have this very short email that basically says, I don't know, it's too difficult or something to that effect, right? I thought about this, but it's a very difficult problem. So, which is interesting because if he replied to me only 3 months later, I suspect that he was thinking about the thing for on and off because the email was sitting in his inbox because he then replied. And so he thought that the problem was interesting, but then at some point he gave up and says, okay, this is too much. And sort of he replied to me so that I'm loading off this problem. I'm not interested in this anymore. So in principle, I think that there is interesting mathematical stuff to be done. It's a little bit, above my level. And then there is also this issue that with this idea of counting states, we saw that I needed non-additive measures, and there was an assumption of additivity here. So maybe that's not exactly what I need. So I just shelved it. And what I'm actually working on right now is a theory of states and processes based on the notion of ensembles. And this is very promising because we have done a lot of results that we saw yesterday. And there are a lot of other open problems there, and so that's what we're mainly going to discuss. I'll give you sort of an overview of what we were trying to do here very quickly, and then we're going to see a lot of the interesting problems that we're trying to solve over there. And those are really at the math level. So if there is anybody here that is really more on the math side, these are really these are a lot of fun. Okay, so first let's go through this information granularity about units and information. And again, the goal is to establish a mathematical precision notion of units, physical dimension, and the required minimal physical assumptions. These are the things that we are actually lacking in math. And a lot of the arguments that we have in reverse physics rely on dimensional analysis and units being treated well. So at some level, we need to do that. And physical dimensions and physical dimensional analysis and so on are a lot more tricky than you would first expect. There are like really a lot of subtleties. And again, it's not clear exactly how you can make a mathematical framework like that. But the idea was basically to have a partial order on all statements. And basically, you're going to be able to say, in some sense, this statement is finer, it's more precise than another or not. And a physical dimension becomes essentially a set of a class of statements that can be compared to each other in a sort of a finite way. So if you have two statements of position, you can compare them and say, oh, this is finer than the other. This gives me more information than the other. But if you have a statement of position and a statement of momentum, you can't compare them. You can't say that one is finer than the other, right? But then you basically need a hierarchy of all of this to be able to sort of define what the physical dimensions are. So some insights, I think, are still valid, and that's kind of why it's sad that I wasn't able to close it. And again, all the notes of all these things are on GitHub, so if somebody wants to resurrect the project, it can actually be resurrected. And so let's look at the basic insight, the things that I do think that are important. So in the topology sigma algebra, it all comes from logical relationships. And so you can say, for example, that the position of the object is between 0 and 1 meters is a narrower statement than the position of the object is between 0 and 1 kilometers, because whenever this is true, this other one is true. So the logical implication essentially tells you that one is valid in fewer cases than the other one. Also, you can say that the third die landed on 1 is a narrower statement than the third die landed on 1 or 2. Again, because essentially this is contained in the other. But note now that this was a statement on geometry. This is a statement in probability. And even this is a statement in information theory. The first bit is 0 and the second bit is 1, is a narrower statement than saying the first bit is 0. So essentially, if a statement is contained in another, then you can compare them through the logic relationship, but that's not it. So if you want to say that the position of the object between 0 and 1 meter is a finer statement, a more precise statement than the position of the object is between 2 and 3 kilometers, you cannot do it through the logical relationship. You need something else. And what is interesting is that this something else is the same, regardless if the precision is a precision in terms of geometry, a precision in terms of probability, and a precision in terms of information theory. Again, this is the whole idea that information is geometry and information is about probability distribution. It's that all these things, they're always the same at a fundamental level. And so again, this is the attempt to say, okay, let's try to find one thing that sort of connects all these aspects. And so the idea is to create, to not only have an operator that allows you to tell you whether something is narrower in this logical sense, but also if something is finer in terms of information content. And the idea is that this has to be a partial order because you cannot always compare things because they might be about things that are incommensurable. So for example, I could have a statement that tells me this is position and momentum. So these are statements of states in phase space. I can say that, the state is this point. The system is at this point. Or I have the statement P that it's the union of two possible cases, so 2 points. And then I have a C that it's a possible range of position. And I have D that it's a possible range of momentum. And I have E that it's a possible range in position of momentum, right? And so we want to be able to say that A is finer than B because knowing that I must be at 1 point is more precise than knowing that I can be in 1 or 2 points. B should be more precise than C, and C should be more precise than E. It's finer than E. But we can't compare C and D. Like there is no sense in which C is finer than D or D is finer than C. And so this basically captures the idea that position and momentum are incommensurable. They are different physical dimensions. Yet the areas of position and momentum can be compared with other areas of position and momentum, and they can be compared with lines in position and lines in momentum. And these are also comparable to points, right? So the issue is that the jump between a line and a surface is going to be some infinite dimensional jump, and that's sort of why you are going to be able to sort of have these classes that sort of work together in this way. And so we would like to basically to say, okay, I have all these statements so that I can all my possible statements on position momentum that correspond to sort of some idealized test procedure. And then you want to be able to choose a unit. I say, A is my units or C is my units and so on. And then you want to be able to find a measure on all the other statements that tell me that, of course, the measure in terms of the unit is 1. And if an object is finer than, if a statement is finer than another statement, then the measure is less. And if 2 statements are disjoint, are incompatible from each other, then the measure sum. And again, you want to be able to do it regardless of what you take, A as unit, C as unit, or E as unit. So that's sort of conceptually what we would like to do. And again, the concept is simple. The realization, I don't know quite how to do it. So there is some part that the basic notions that we did was essentially copying in some sense or stealing from what De Finetti started in the 19th century with this idea of defining probability from the idea that you can take 2 events and say, I find this less likely than that. Right, so this whole idea of defining probability of the propensity of betting on one to the other was essentially started by him with the idea that you're basically putting a pre-order on these statements mathematically, and then you show under what condition that pre-order becomes an order, then becomes a measure. And so this is essentially what we say. We're going to have some theoretical domain, like we had defined from the topologies and the sigma algebra from the verifiable statement. You have a relationship that takes two statements and tells you true or false, right? It tells you whether one is finer than another. You want this to be bounded in the sense that if you have a contingent statement, something that could be true and could be false, then it's always coarser than the impossible statement, the one that always is false, and it's finer than the certainty, the one that is always true, right? So you want this thing to always be in the middle of these two. You want this relationship to be transitive in the sense that if a statement is finer than another statement and the statement 2 is finer than 3, then the first is finer than the third. And you want to have this offset monotonicity, meaning that if you have a statement that it's incompatible with 1 and incompatible with 2, right? Then if S1 is finer than S2, then it must be the case, there is an if and only if, that if you make the disjunction of both statements with the other thing. So if you think in terms of sets, you have a set that is disjoint from two sets, then the measure on the union of the first set with one and first set with the other has to have the same I can say size relationship between the two statements, the two sets by themselves. So essentially, adding a set by a constant should give you the same result. So if you have two statements that are this coarser than the other, and I'm moving them up by the same amount, they are still one coarser than the other. So this is basically what it does. And just with these three things, it turns out that you can prove a lot of things. You can prove that this fineness is a preorder, which is the type of objects that the Finetti starts with. You can then define equigranular classes, so classes of statements that are all at the same level of information, let's say, than each other. And then you can make a map between the statement and one of these equigranularity class, and this is an order homomorphism, which allows you to do something. So there are a lot of things that sort of work out, and the nice thing is that these are minimal assumptions, and it gives you many consequences, so it always tells you that you're on the right set and in the right direction. The problem is that we still have no idea to generate how to get to the measure. The main problem, again, you would like to take a unit statement and then define a measure that for every other statement gives you some notion of size. The problem is that you need some conditions for this measure to be unique, and we do not know what those conditions are. And it's clear that you cannot define this on the full space because some of things are going to be incommensurable. So if I took a statement on position, I'm not going to be able to compare it to a statement in measurement, so I'm not going to be able to put a measure on those statements. And it's not clear how you define this algebra of comparable statements to the unit and whether that is unique. And so there are a lot of problems that needs to be understood in terms of what are the necessary and sufficient condition. I had actually an undergrad student actually he was quite good, because at the first year he could already like futz around with these things. We actually were able to show that you needed some constraint on the actual topology, like the topology would need to have enough sets to be able to talk about this, because we were able to say, okay, let's take this set, let's throw a lot of let's take this space, throw a lot of things out. Can we still say the same thing that we were able to say before with all the sets and all the points? And the answer was no, you can't. Therefore, you need some of these constraints. So this is sort of a very open problem, and it's sort of the boundary of logic and measure theory, which probably is not the cup of tea of most people that are watching this, but it's something that again, in principle, I'd like to make some progress on and understand. Now, another thing that I said before is that we need, with physical mathematics, to reconstruct everything. And one of the things that we need is the notion of differentiability that maps well to the math, but also that it's physically meaningful. And this is, again, where we have a prototype that I think works, but needs to be finalized compared to the current literature. I want to have a convenient notation that allows me to do certain things, and I want to be able to see whether the same notion of derivative can be used to generalize a lot of other notion derivatives. I'd like to have one derivative to rule them all. So that's basically the goal. And again, this is it's more on the sort of not pure math in sense of pure math side, but it's more on the math side than on the physics side. One of the things that I already mentioned is that the way that things are defined in differential geometry right now, they're a little bit unintuitive for us physicists. And actually, it seems that they're also unintuitive for a lot of people in the math, because I was at a topology conference once, and I asked the grad students, why are you in topology and not other things? And they said, well, I'm definitely not in differential geometry because all the definitions do not make sense to me. And that was a mathematician that does topology, which is also very abstract. So they didn't make sense to him. So, okay. So like very simply, a differentiable manifold is a manifold that means something that you can sort of chart with real numbers, plus a differentiable structure. And the differentiable structure means that all these these coordinates that you can use have a differentiable transformation among each other. And this definition of differentiability is the notion of the Frechet derivative. That's what you use behind the hood. So you have a notion of differential and a notion of derivative that is based on the Frechet derivative. Then what you do is define vectors as derivation of scalar functions, as we saw yesterday. Basically, the bases become the derivatives, and then you sum these derivatives in a different direction, and that gives you the vector space. And the differentials are linear functions of the vector. So a differential is something that takes a vectors and give you a real number. And so you write things like this. You have dx of v, but v that you're writing in coordinates, and now this becomes the x component of v. And when you go in, you integrate these differential forms. So you're integrating functions of the vectors. And this sort of does not make sense physically. Like literally, velocity is not a derivation. Momentum is not a function of derivation. Derivations depend on units and cannot be summed, so they don't form a vector space if we give units to the parameters along which we're doing the derivation, which we have to do in physics. So you have two mathematical notion of differentials and sort of way to derive. One that is hidden between the coordinate, among the coordinates, and one that it's defined in here, which I think makes it a little bit strange. And then there is always the idea that in this math things, you define the infinitesimal things like the differentials, and then you define the integration. And we would like to have exactly the opposite in physics. And we have the finite things, and the infinitesimal thing are the limit of some decomposition that becomes, there's something that you're getting smaller and smaller. And so what we'd like to have is a notion of differentials and so on that mimics more what's there in so when you do vector calculus and this type of things, the idea of displacements and these type of things that make more sense. And we also want these things to mimic also what happens in variational calculus, which is more similar to the older way of doing differentials and derivatives. And nothing. We would like all these things to mesh together well. Conceptually, the idea is this. Let's say that you have three spaces. You have time, space, and temperature. You're going to have a trajectory, which is a space as a function of time. And then you're going to have temperature, a temperature field, a scalar field, which is the temperature as a function of the position. you want to be able to say that there are some notion of differential, of things that are becoming small, and then the velocity is the map that maps an infinitesimal change in time to an infinitesimal change in space, right? So if I give you a small change in time, I multiply by the velocity, I get an infinitesimal change in space. Same thing, this you can think it as the derivative of this function. Now, from a small change in space, you're going to get a small change in temperature. And this is just the gradient. So you see, this is the vector. The vector is something that it's linking this differential to this differential. And this is a covector, but it's still something that is mapping a differential to a differential. And in general, in physics, the idea is that any tensor that we have, like the tensors that we have in special relativity and so on, those types of tensors, they're the one defined on the geometry, are just maps from spaces of differential to spaces of differential. And even the coordinate basis, right, the thing that we think as coordinate basis is not really a vector field, but it's not really a space of vectors that we're doing. We're not summing vectors here. We have differentials that are defined on coordinates, so they're defined on a particular space. And then we have a differential defined on a manifold that it's the unit-free change. I go from this point to this point. And the basis, the coordinate basis, is a map that takes an infinitesimal change in the coordinate, the thing that has the unit, and gives you an infinitesimal change on the thing that does not have the coordinate, and it's unit-free. And so if we cast everything in this way, then we can have a notion of differentials, derivative, and tensor that is still mathematically precise, but it maps so much better to the physics, such that when we go and look at the geometry of phase space and all these things, they actually make sense. Like you can look at the symbol and say, okay, I understand what's going on. And this is also the type of thing that I'd like to extend, such that when we work on field theories, we essentially use the same thing with the same notation. It's just that now this space is not just a manifold, but it's a space of function. And it's a spatial function where we're going to be able to define infinitesimal change, and we're going to have functions from a function space to a function space, and we're going to be able to take a derivative because we're going to ask how much this infinitesimal change on the initial space becomes an infinitesimal change in the target space, right? So this is conceptually what I like to have. And of course, the problem is defining a set of details that are clever details that allow you to do this. The first clever detail is to basically say, I have these things that I call convergence envelopes. They're a sequence of non-zero on R that go to zero. And so these convergence envelopes tells you how you're going to zero when you're making this limit of pieces that become smaller and smaller and smaller. And then you can define a differential as a sequence of vectors such that there exists a convergence envelope such that when you take the limit of the sequence of vectors divided by that convergence envelope, you get a final vectors, which is the tangent vectors. What it means physically is that you can imagine that you're getting these vectors that are becoming smaller and smaller and smaller and smaller, but as they go to zero along a particular direction. For example, they don't keep spiraling out, right? That would not give you a differential in the real space because this limit here would not be defined. The cool thing about defining things like this is that this is the only division that you're going to have. You're not going to have only division with the scalar. So when we're going to, when in the typical way naive way that you define the derivative, you have a division between differentials. We are not dividing a differential between another. We are defining this differential where we have vectors divided by scalars because we are not going to be able to divide vectors. And the other cool thing is that the only thing that we need here is the vector space structure and the topology that tells me what limits are are used. And this is exactly the type of things that one has when you do variational calculus and you work on function spaces, because you don't have the manifold structure. And so now you can show that every differential can be seen as a sequence where there is a constant here, which is a tangent vector. There are w's I that go to 0, and you have the convergence envelope. So you basically are rescaling t smaller, 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 but then you have this extra error, right? When you are thinking that you just have t, that goes to 0 at infinity. And this is how you can think of your differential. You could define it like this, you would get the same thing. And then you can show that you can have this notation that you basically say this is a differential with convergence envelope AI and tangent vector KT. And you can, of course, take the K and move it from the tangent vector to the AI. And this is some useful property that you can use for calculation. What you can then show is that if you fix your AI, you get a vector space. So all these differential make essentially what I would call a tangent space. So the tangent space, it's not the space of derivation, it's the space of these sequences that go to 0 in a particular way. And then what you can do is, we're not going to have time to go through the details, but you can define a notion of derivative. And what basically the way that it works is that you have a function that maps a point to a point, a vector to another vector. And when is applied to a differential, you basically, the convergence envelope remains the same. So you go to 0 in the same way in the original space and the target space. And the tangent vectors only depend, the final tangent vector only depends on the initial tangent vectors. That's basically what you're requiring. You're mapping a differential from a differential. The convergence, the way that you go to 0 is the same, and which direction you go to 0 only depends on the initial direction where you were going to 0. And what you can find is that these derivatives must be a linear function. And again, this is interesting because a lot of the generalization of derivatives like Fréchet and others, you kind of have to impose somewhere that they are linear, and we get R for free because we're allowing these essentially to, when you are approaching your point, you can approach it however you want, and that makes basically the linearity is equivalent to that. You can define a chain rule, and the chain rule becomes simply a function composition. So if you're mapping from first space, second space to third space, or you map directly, and if these two are differentiable, then also the final one is differentiable, and it has to be the composition of the two. And again, what is cool is that the proof goes through very smoothly without very many constraints that you require. You recover the standard notion of derivative from R to R and the notion of a Fréchet derivative. And again, you recover this idea that if I have two manifolds and I have local coordinates, I have map between the manifolds, but I can also express the map in local coordinates. And the thing that you recover are the things that you would expect. And as I said before, you have a differential that is coordinate independent. You have differentials on the coordinates that depend on the unit, and the bases are the maps that you use to go from coordinates from differential on coordinates to differential on the space. Again, this is essentially what we do in physics. The vector space structure is here. It's not, and it's among these maps. It's not among these maps and these coefficients as you would expect when you look at this. It's not that this is a basis and these are numbers that we're multiplying the vectors, that they were multiplying the vectors to, because otherwise this dimension would not make sense. This is a map, and we're mapping things from different coordinates. Again, another thing that we kind of talked about yesterday is the idea that differential forms are sort of taking things that are defined on finite regions and dividing them up into infinitesimal pieces. I think that notion of derivative could be adapted to work on here as well. The vector space become the spaces of multivectors in some sense. So this would connect to some of the ideas that are there in I forget the name, but the notion of the geometry, the notion of geometry that we were talking about in the first day. But again, I think it's going to map the whole details needs to be done. So, but let's skip now to the more physical things. But again, if somebody is interested in sort of this foundational question, I'm really trying to find somebody who can help me figure these things out, because I'd like to have, as I said, one derivative to raw, that it's meaningless, and then it's meaningful, that it's physically meaningful, and then we can sort of reinterpret a lot of the things that we have in classical mechanics and classical field theory, E&M, like reinterpret all of that such that we have geometrical notion of what the electromagnetic fields are, how they become tensors in GR, right, and all this. I'd really like to have those things. But anyway, and everything that we need, as we saw yesterday, we can have this notion of ensembles, and we know that ensembles must have a topology, and the ensembles must mix when we're doing statistical mixtures. Therefore, they give us a convex space. A convex space with a topology, and again, in the literature, there is no literature about topological convex space. There is literature about topological vector space, because that's what they use in analysis, but not about this. So we need basically to bridge this gap to understand how you go from one to the other. And so basically what we're trying to understand here is, first of all, how can we take, what are the necessary sufficient conditions for a topological convex space to embed in a topological vector space, and whether ensemble spaces already satisfy those requirements, or we need some other additional structure that may or may not be true for all physical theories. And then what we want to understand is what the result that are there in topological vector spaces can be generalized to topological convex spaces. My hunch, this should be a lot, but again, it's not a matter of mathematical detail, and yeah. And so let's see, what are the things that these things we already saw yesterday, that the use of topology is what allows us to extend the finite combination to infinite one, which is the same thing that one does for topological vector spaces. And we do have, I have a lot of conjectures that I am trying to prove, and we actually have an undergrad right now that is working for me over the summer to see if we can prove them or not. In fact, I think there is a part of this, one of this conjecture that we already proved that it's wrong. But anyway, one of the things, for example, that we would like to understand is if I have a sequence of an infinite mixture that converges, whether I can take out the first element and the thing still converges. Intuitively, it would make sense to me that that's the case, but again, you need to prove it. And the same way that if you have an infinite sequence that converges, can you split it into two separate infinite sequences that converge? Like, I have no idea. Maybe that you can't. I don't know. Another thing is whether if you take a set of ensembles, and then you make all the possible mixture for those ensembles, and then you take all the limits that those ensembles can allow you to have, is whether you are still closed under a convex combination, so that when you make the topological closure, you preserve the closure on the convex structure. Now, this is true for in the vector space. If you take a convex vector, a convex subset in a vector space, and you do the topological closure, you still have something that is convex. And so I kind of think that that's going to happen here in topological convex spaces, but again, it needs to be proved. And one of the ways that you do it is, if you like math, you go and look at what they do in the other spaces and see if you can find a proof that does not use all linear combination, but you can sort of use only the convex combinations to sort of get the same result. Now, yesterday we saw that there are these conservative convex spaces, and they embed in a vector space. And now the question is, when is this embedding continuously? So can you have a T1 second countable cancellative topological vector space embed non-continuously in a topological vector space? Maybe you can, maybe you can't. If you can't, then it means that as soon as you have a topology on your convex space, and you know that the convex space embeds in a vector space, then you already have a unique topology over there, which would be interesting to know whether that is true or not. And again, one of the things that is true in topological vector space is that finite dimensional topological vector space with the same dimensions are isomorphic in the sense that you have a unique topology. So for example, if you take Rn has a unique topology that makes the sum and the multiplication continuous in that vector space. That is why finite dimensional spaces are so nice, because there is only one possible criteria of convergence, one possible way to essentially define a metric. Everything is nice. When you go to infinity, this is where things become a lot harder. So one of the first things to settle would be, suppose that I have some finite dimensional topological convex space, or a convex space that embeds in a finite dimensional vector space. Do I have a unique topology for the convex space or not? Right? That already is, for example, related to the previous questions in a simpler case. But those are the type of questions that need to be settled. That again, the physical meaning would be that a particular class of ensemble spaces, once they are defined, they would have a single criteria of convergence. It wouldn't matter what the ensemble space is, as long as you can think it of that there are finitely many things that you can mix together. You get you get all this stuff for free. So that would be interesting to know. One other thing that we have identified is that all the bad things seem to be happening at the edges, on the extreme points of the convex space. And the question is whether that's the only thing that bad things that can happen. So if you throw away sort of these edges, everything maybe starts to be nice. I have a suspicion that that's the case, but that's what needs to be proven essentially. So that's part of it. The other thing that we had looked a little bit yesterday is this notion of entropy defines the geometry of the ensemble spaces, and the goal here would be to derive all geometric structure from a definition of entropy. And we saw that in reverse physics, all the geometric structure in physics are related to entropy, and so we want to essentially show that the entropy defines all possible types of geometry that we have on ensemble spaces and also outside of ensemble spaces. We saw that there was this notion of distance that you can define. You take two ensembles and you say, I make an equal mixture of them and I see how much the entropy goes up. This was a nice quantity that it's almost a pseudo distance, but it's also a distance, but it does not satisfy the triangular inequality. What happens is that in both classical and quantum mechanics, this is the Jensen-Shannon divergence, and it's not a distance, but it's the square of the distance function. And so the question is that true for ensemble spaces or for a specific class of ensemble spaces where everything can be decomposed in orthogonal elements? And if this would be true, then again, it would be like a generalization or a result that we were having classical and quantum mechanics, and it would severely constrain the type of spaces that you can have. Another thing that we can do with this distance function, and we can show already with the distance function, is that if you take a point and you make it go an ensemble, as long as it goes closer to this to another ensemble, then this mixing entropy essentially goes to zero, and goes to zero in a continuous way. And so the question is whether this mixing entropy recovers the convergence criteria of the space. So it is true that for every sequence of AI that converges to A, and then it is true that the entropy, this mixing entropy, goes to zero. but is the reverse true? So we can prove the in one direction, can we prove the other side? If this would be the case, then what would happen is that the geometry, like the entropy, this geometry defined by the entropy, also defines the topology based on essentially open ball of entropic distance from different points. And that would very likely give us then a metrizable space. And so we would basically say that all the spaces that are physically relevant are metrizable, and the metric is essentially derivable from the entropy. Now, this is true for classical spaces and quantum spaces. The question is it true for all possible physical theories? And if we had that result, it would be a very strong result that basically would solidify this idea that entropy is geometry. Not only entropy is geometry, but it's exactly the geometry that defines the topology and the criteria of convergence. Now, these are samples of, this is a classical discrete space. This is 1, 2, 3. These are the 3 possible cases. And every point in the triangle becomes a probability distribution. If you are on this side, you have a probability distribution between 1 and 3. If you're in the middle, you have a probability distribution that it's equal, 50% one and 50% the other. So any point in the space here is a distribution between a probability distribution between 3 elements. So A and B are 2 probability distributions, and this is the set of all the other distribution that have this entropic distance less than 0.04. So these are balls, let's say, of a particular defined entropic distance. And what you can see here clearly, these are convex sets. Also, if you do the same thing in quantum mechanics, this is a section of the Bloch sphere. And so every point inside the Bloch sphere is a probability distribution, a mixed state. If you take 2 points, then again, these are the open balls of the entropic distance with the same value. And again, you can see that these are convex sets. Like they don't have a kink like this. If you take 2 points, you always remain inside. And so the conjecture is, are all the entropic open balls convex in classical mechanics and quantum mechanics? Can we actually prove it instead of just drawing pictures? And does this generalize to all possible ensemble spaces? And I tried putting a different entropy function that it never gives you anything orthogonal, and you can come up with things that satisfy the axiom, but they give you balls that are definitely not convex. So probably we can't, with the axiom that we have right now in general, prove that these balls are always convex. But maybe if the space again is orthogonally decomposable, you can always do it. I don't know. That this is the part of things that needs to be understood. And the question of whether it matters is if we had, if we have the topology that is generated by these entropic balls and these are convex, then we have a locally convex topological vector space. It means that we have another set of properties. In fact, the locally convex topological vector space are usually the one where you define derivatives, because derivatives in topological vector spaces that are not locally convex give you some weird features that you do not. So if the entropy not only gave us a geometric metrizable space, but also made sure that the space were locally convex, and then we would be doing a lot of things, and that would be again an interesting physical mathematical results. Another thing that we saw last time is that if you make this distance applied to infinitesimal, you're going to get essentially a metric space, and you're going to have sort of a Riemannian geometry type thing. And we want again this to work in infinite dimension, and we would need a way to define this differential infinite dimension in a way that is consistent, that we would like, that makes physical sense. And so this is sort of part of the extension of the notion of differentiability, and that's why I want to have a nice notion of differentiability so that I can say and do these things precisely in the physical mathematical side. And then there are other problems that are even more ill-defined, because a lot of the time in this type of research, defining and finding the right problem is actually the problem. Once you figured out what is it that are the proper axiom and proper starting point, things become easy. So one of the questions is how does the geometry of the space of ensembles relate to the geometry of the spaces of states? So this is completely unclear. Then whether, with this mixing entropy is a number from 0 to 1, it kind of reminds you of an inner product. Does it mean that we always need an inner product in these spaces? So any physical theory has an inner product space? Again, I don't know. And then whether we can generalize some results from entropic geometry to ensemble spaces. So this is sort of some of the pieces that we want to do in information geometry. We want to have a general notion of measure theory. As we saw before, we were able to define this notion of non-additive measures by basically looking for operation in the convex space. In classical probability, you have a probability space with the sample space, a sigma algebra, and a probability measure. You have a state count, which is a measure of the sigma algebra, and then you can define derivatives as essentially probability densities as derivative between the probability and the count of states. And then you can have random variables that are defined on the points, and then you do expectation by integrating the function with respect to the probability, with respect to the state count. Right? This is the structure that we have in essentially in classical theory that is very measure theoretic. And this is exactly the structure that does not work in general for quantum mechanics. And so what we'd like to have is a generalization of this structure that would also work in quantum mechanics, and therefore it would need something that is not an additive measure. One way of looking at this is that when we talk about probability, an additive probability is really a probability of outcome. When we do probability in terms of mixing operation, that is something different. And the idea is that the mixing, the measure that we want to define is on this side and not on this side. And so, as we showed yesterday, we can define a state capacity. If I have a set of ensembles, I can say that this set of ensembles is defined on these many distinguishable states by looking at the supremum of the exponential of the entropy of all the possible convex combination. And we can show that this is a non-additive measure. In the same way, you can ask if you have a set of mixtures, a set of ensembles, you want to ask what is the biggest part of this ensemble that I can get from a mixture of these other ensembles. This gives you a coefficient, which we call the fraction capacity. And again, this is a non-additive probability measure in the sense that it goes from 0 to 1 in terms of the value, and it's 1 for the full space. And so we can define on the space of ensembles statistical quantities as those quantities that are linear with respect of a convex combination, and therefore they essentially are expectation values. An expectation value of a mixture is going to be the mixture, the average of the expectation value. And this means that we can have classical operator and quantum operators of expectation value look the same, even though they're implemented differently. In the classical case, it's going to be an integral of some probability distribution. In quantum case, it's going to be the trace of some density operator. But to the sort of more abstract level, these are just linear operations that are real value functions that are linear in terms of the convex mixture. So we can define these in a more abstract way. What we still needs to be proved is that we can go the other way around. If we have a classical space and we define a linear operation on the ensembles, can this be represented as the average of something? And it most likely is true, but we need still to do the due diligence. And so once you have this, all of this, you would like to be able to say, okay, I have a state capacity, which is the generalization of the Liouville measure that counts the state. I have the fraction capacity, which is a generalization of my probability measure. I want to be able to define some sort of derivative between the two so that I can define a probability density. And I want to be able to have some sort of integral such that when I take this function and apply it to multiplied by this probability density and I make the integral, I actually am doing the expectation value and recovers the linear operation, so that all linear operator can be written in such a way. I have no idea if this is possible. As I said in the question before, I hoped that the non-additive measure literature would give me a result in terms of these things, but it seems that all the features that we are trying to use do not satisfy the requirement of this. In fact, this is here. There are already non-additive measure theoretic tools. There is fuzzy measure theory. There is a Choquet integral and Sugeno integral that are all defined on fuzzy measure that are a generalization of additive measure to non-additive case. Unfortunately, these don't seem to be the right one, which is sad on one side. On the other side means that it's probably new math to be developed, which probably to be interested, but then I have to find mathematicians that help me to do that. The last thing that we're missing on the ensemble space that I know we are missing are some type of Poisson structure that tells us that we have conjugate variables. I do not have a way to do that right now, and probably it's something that needs an extra axiom, but it needs an extra axiom that is compatible with the things that we're already doing. So very quickly, because we don't have much time, the idea is that both classical mechanics and quantum mechanics is that you are going to have an ensembles, and you're moving an ensembles, and you have H, that is the generator of a transformation, and T, the parameter of the transformation. You're going to have observables, and you're looking at how the observable change in time. In classical mechanics, you use the Poisson bracket, and in quantum mechanics, you use the commutator. And both of these are skew-symmetric brackets that tell you how variables and observable change during the transformation. So this is what we need to generalize, this idea that we have transformations and conjugate variables and generators and so on. And again, we saw that we have already a way to generalize statistical properties, right? So we have that in the classical case, it would be the integral of the density, and in the quantum case would be the trace of the operator and the density matrix. And so the way that we can generalize the bracket is essentially making the expectation value of the bracket. So on the ensemble space, we define the bracket, the skew-symmetric bracket, that in the classical case should reduce to the Poisson bracket, the expectation of the Poisson bracket, and in the quantum case should be the expectation of the commutator. So this is basically what we like to generalize. And what you can show that this defined in both cases would give you the structure of a Lie algebra. And so this generalized thing, either we derive it or we have to define it to be a Lie algebra, since this is the structure that most likely we're going to have. What it doesn't seem to be, it doesn't seem to be a Poisson bracket, because the Poisson bracket has to act as a derivation on an associative product, and it's not clear to me what the associative product should be, because the expectation of the product is not the product of the expectation. And since we only know how to make operation on expectations, because those are the numbers that we have, those are not going to be the products that the Poisson bracket, for example, sees. And so the question is whether this product can be defined in terms of the generators of composed transformation, and whether the non-commutativity of variables itself can be the non-commutativity of composed transformation, and whether the lack of the relationship between the expectation of the product and the commutativity is what we're looking for. So these are all things that I still have to wrap my head around, and so I'm, it's somebody likes Lie derivatives and Lie algebras and so on. These are the type of things that I'm looking at a more fundamental level. Okay. Right, then it's the question of whether we have an axiom. Right. So one of the way to look at this is that these are both a deterministic and reversible transformation because they leave the entropy unchanged. So there is a compatibility between this algebra and the entropy itself. And also, this structure guarantees us that there are always stationary ensembles under each deterministic and reversible evolution. So if you have this structure, you can create ensembles that are Boltzmann distributions and are going to be left alone. They are going to be equilibria of the transformation generated by H. And so the question is, can we turn it around? So we already assumed that the ensembles must be equilibria to have an entropy well-defined. He's assuming that every ensemble is a stationary state of some time of evolution, enough to say that there must be this structure, because I will have a generator for my evolution because I'm in a linear space anyway, so that I can define a Lie algebra like that. And then I want to say every state must be kept the same. Therefore, there must be a quantity whose average cannot be changed, because that quantity is gonna tell me that I have these states that are equilibria. And therefore, maybe there is a way to recover this from a more conceptual physical premise that is sort of compatible with all the things that we already said. So anyway, wrapping it up. So it should be clear that we believe that it's possible to create a solid mathematical framework for all of this that starts from these physical axioms. We just need to figure out exactly what these axioms are and how they're structured. And we also need to construct all the needed mathematics from the ground up. So we basically are at topology. We need to build a lot of our things. And to be able to do that, sometimes it means that we're reorganizing core mathematical ideas that are already present in a different way. But sometimes we have to define a new math. So for example, for the differentiability, I think it's more like reorganizing things that we already have. But for topological convex spaces, those do not exist. Though it's a small step, but probably for the non-additive measure theory in the way that we need it, that's probably a much bigger step. That's really new math that needs to be done. And again, we need to span multiple branches of math and physics. So I'm always very interested to talk to people who are more mathematically inclined than me, and that can help me guide for this region. And as before, the simplest thing that you can do is sort of fill in this form and say, oh, I know about this type of math, this type of physics, I can help there. And if you instead want to be more involved, you reach out, and then we'll figure out something. And again, this was the hour, so I'll stop.
Right. We've got a couple of questions. So from Daryl, for the measure of granularity, what is the sigma algebra you define the measure on?
So we have a sigma algebra that comes from the experimental domain, which basically are all these statements that are theoretical and stuff. So if all statements are comparable to each other, then that's always going to be the sigma algebra for everything. The issue is when they're not comparable. When they're not comparable, say some statements are statements or positions, some states around momentum, I do not know how to define it. Because in principle, you could say, I start with my unit, my statement that I take as a unit. And of course, the unit is comparable to itself, and I need to be able to give a value for the unit. So I need that. And then you start finding all the other sets and statements that are comparable to it, and then you can grow this sigma algebra. The problem is that there is no I can say that there's no we're not able to show that if you with such procedure you would get a unique sigma algebra. You could be that you grow it in one direction, and then some statements now are incompatible with some other statement, though they were still comparable with the unit. So we do not know what are the set of necessary and sufficient conditions to define that sigma algebra. We have some intuitive ideas in simple cases, but how to do it in general, it's not completely clear. Sad.
Next question is from Xinyue. There are multiple ways in differential geometry to introduce tangent vectors as differentials. I think the ones using function germs to define cotangent vector space first are more close to what's being described here. For context, this method also generalizes spatial differential from differential on parameterized path.
And let me look at the thing. Could be. I'm not familiar with that. That's exactly why I was saying that there might be things that are already very similar that have funny names, and so I'm not aware of them. But yeah, I'm not. I'm not saying that the thing that I'm doing is completely new. I think this trick that makes the derivative automatically linear, it's if not new, at least buried in some paper and nobody's paying attention. But yeah, so this would be the type of work that is needed. Going and look at the literature and see if he exactly is that or not.
Anytime we can find something that's already developed that we weren't aware of, that's great.
Oh, yeah.
Because it saves a lot of work.
Yeah, so this is where, again, I want to use, as I said already, as much as possible things that are already there. If I can just take the math that already exists, but sort of change maybe some symbols so that it's more palatable, I would just do that. Or if you can take it right away as it is, it's also. So topology, most of it, it's fine. Once we just say that it's second countable, anti-zero, it's exactly what we need. Even measure theory is very close. For differentiability, it's a problem of what gets decided to be mainstream, right? So most of the standard differential geometry book use this algebraic notion of tangent space. So that's it.
Next question is from Leandro. The Lie derivative is purely topological. The covariant derivative encodes geometrical information. If I understood correctly, you would like to have a single framework for derivatives, ideally with a notion of derivative which works in all physical cases. Is that correct? If so, to which extent would you like to pursue this search in the context of field theory, given these fundamental distinctions?
Good question. In the way that it's going to work, which I don't know what it is. So the problem with the theory is this notion of the infinite dimension, the infinite dimensional problem, where you have the different criteria of convergence. So what we were able to show, for example, that might be some that might be inside this whole mess. A lot of the ways that one standard trick that it's used on topological vector spaces is essentially to have enough linear functionals that allows you to define the points, and then you have the idea, for example, that you have the states, you have the quantities, the variables, which are going to be linear function of those states of the ensembles. And then you can sort of then also do it twice. The state now is a linear functional of the expectation. And you can do these tricks. And you can do these tricks if you're using essentially the topology induced by the linear functionals, which gives you a certain type of convergence. What we have seen is that the convergence that you at least need for the entropy, because we have this notion of distance, so at least the notion of distance has to be zero. So whatever other criteria of convergence that you have, it has to be stronger than the one that tells you that the entropy goes to zero, is in general stronger than the criteria of convergence that you have on the linear functional themselves. So the thing that is defining probably the geometry, which would be the entropy, is also defining a criteria of convergence that is very strong. And so there is something there that it's all connected, but I don't know what it is. And again, if I had a mathematician that knew all the possible things that I should be looking at, and then we can sit together for like half an hour. Did you look at this? No. Did you look at this? Yes, and so on. Then the whole problem would go on a lot faster. But even with the mathematicians that I talk to and we collaborate with, they are not expert in this subfield, because all these things become very, very technical very, very quickly. And so it's a process. So the question is, right now, I don't know. If you know how to help figure it out, let me know. I'd be gladly happy to have a talk. And also, to be clear, yeah, I'm not a mathematician, so a lot of these things that I do, it's sort of half as a hobbyist, but I still I need to do it with enough technical expertise to at least be able to talk to an expert, so that the expert that I can understand what the expert is telling me, and I can understand what are the problems as they are. But it might be that, me personally, I can bring the problem only up to a level, but then when an expert will have enough understanding, like I will have specified the mathematical problem enough such that there is a unique solution. The problem is always there. Like going back to this quote from Sabine Hossenfelder, like she says, the physicists make a mess of things, and then it's up to the mathematician to clean it up. And it's okay only if you gave to the mathematician enough instruction such that the mathematician can tell you, yeah, I only have one way to clean it up. If you have multiple way of cleaning it up, then it has to go back to the physicist, and the mathematician has to ask, okay, physicist, in which way do you want me to clean it up? Because there are different choices.
Currently, no other questions.
Yeah, let's wait another couple of minutes if people, there you go.
All right, Daryl asks, I think there are notions of convergence that are more general than topology. Topological spaces have a canonical convergence, but there are convergent spaces which do not come from any topological spaces. How do we get the topology from the convergence for entropy bubbles?
Okay, let me think. Because I stumbled upon this, but I don't remember what I concluded. I don't remember what I concluded. You're right. So I did stumble into this problem, and so the answer was that, let's see. So let's think about it. So we do have a topology, because the topology comes from experimental verifiability. So we are going to have a convergence criteria for the topology. That's sort of, we need to have it because that's what we're getting just by saying that the theory has a basis in evidential, in experimental verifiability. The notion of a topology that the motion of limit that you get from there, it actually is conceptually very sensible, because you have, let's say that you have a limit, right? So you can imagine physically you have something that it's getting closer to something, and then you want to know whether you are you are getting close to that point. And every neighborhood of that point is a verifiable statement that is true if you are in that case. And so what you're basically saying is that, well, you have your sequence of cases that are going closer to the one that is the limit. And therefore, you're going to have a sequence of true false, or whether that verifiable statement is true or false. And what's going to happen if the point is a limit is that at some point that statement is going to become true, and it's always going to become true. So your sequence of points gets to the points where all the verifiable statements are starting to all settle, and they're all going to become the true or false, exactly like if you are in that point. You just need to wait that the sequence sort of goes in, and so I think, to me, that's the sensible way to see to look at convergence. Now, I forgot. Like, I must have looked at this months ago, and now I completely forgot. What was the examples? A further question is, then it is a conjecture that the topological space is metrizable. So the conjecture of whether it's metrizable comes from the topological vector space case. So if I have a topological vector space that it's T1 and second countable, it's automatically metrizable. So we have now a topological convex space, right? So a topological vector space. We know that it's T1 because these entropic open ball, you can make them equal to 0, and then that's going to have a singleton, and then therefore that singleton is closed. So you know that every singleton is closed, so you know that you have T1. If it is true, even in convex spaces, that if you have a T1 topological convex space that is second countable, which we must have by axiom, you are metrizable, then we would have a metrizable space, right? So these are the pieces that we need to check. And then if it's metrizable, if I knew that it were metrizable, I think I can prove that the entropic open balls are a basis, are a local basis of the point that you fix as neighbor. So for the Gödel incompleteness spheres, I should probably repeat the questions, because the people who are on YouTube are not going to hear it. So the question is, do you foresee some sort of Gödel incompleteness problem affecting physical mathematics or reverse physics down the line? No, because the way that Gödel's theorem works is that you need to be able to construct a statement that is also about a statement. You basically need to have this recursive nature. And the way that we have structured physical mathematics and all of this is that you have the set of statements, but the meta statements, like the statements that are the physical theory, like that are the ones that are connected to experimental verification. But the meta statements are not of the same type. They are the sort of in the meta language, in the language that you use to describe the theory. They're not elements of the theory themselves. It's like, and this is by design, because you are not going to be closed with experimental verification when you go on the meta statement. So I might be able to say that to measure whether the mass of the electron is within a certain bound, right? And so that's a statement that has an experimental test associated with it. But if you wanted to ask the question of whether that statement is a certainty, means that it can never be false, right? And that would be an element in the meta language of the theory that we would have. That statement does not have you're not guaranteed experimental verification. In general, when you have the quantifiers, like the for all and there exists, even if you have you're able to make the statement verifiable for one case, once you add the quantifier, you're not necessarily guaranteed that that statement is verifiable or not. So you can say this electron has the mass between these ranges, but then saying, since I know how to measure the mass of an electron, I know how to measure the fact that all electrons have the same mass. That's a leap that it's completely different. So there are a lot of things that you can do in logic when you're assembling statements that you can't do with retaining verifiability. Essentially, the only thing that you can retain while doing verifiability are the finite conjunction and the countable disjunction. You can't do anything else. And if you only have those things, and those are the only things that you're guaranteed to have, you can't construct a Gödel sentence. You can't. And so all the things that allow you to define, the numbers and all of that are sort of meta constraints, which are the assumptions from which you derive the set of statements. But then the set of statements that you can have in the theory is still closed in a much smaller way than the Gödel completely would allow you to do. So basically, the way that I put it is that the problem, like the things that you can do with experimental verifiability and experimental verification are so much more constrained and so much less rich that you're going to end up hitting other problems before you can actually hit the Gödel incompleteness theory. So I hope this gives you a sense. It's similar to what we said the other day. The fact that since we don't care about all possible sets, we only care about the sets that can be constructed with these theoretical statements. So the sets that can be associated with an experimental set. Therefore, we only care about the Borel algebra of a topological space. That protects us from the problem in measure theory, the Banach-Tarski paradox, and all that. So here is the same thing at a logical level. We can do very few things, and therefore you can't construct this paradoxical thing because you really can't. You don't have the tools to do it. And again, if there is a mathematician that wants to make this argument precise so that we can make it in a paper, that's also part of the things that we can do. Let's give it another half a minute to see if there's anybody else who is. You also need the time to come up with questions and digest all the hundreds of things that I've thrown at. Okay, we close it here then. Thank you for all of you guys for having stayed up to this time. And again, if anybody else wants to be more involved, let me know. We have the Discord where we can discuss some of these things. If somebody wants to have some follow-up discussions on a live so that we can actually talk in person and not just for a chat, I'm welcome to do it. And if you tell other people that this project exists, that would also be useful. And thanks again.
Thank you.
Okay. Bye, everybody. I'll close the live.